I will begin with a word of prayer. Is the audio working? I forgot if I pressed the... Okay, excellent. Dear Father, we thank you for this day. And Lord, I thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So today is exciting. We are going to talk about the... what lecture is this? Forget. Lecture 15, which is going to be on the so-called first isomorphism theorem. Although, you're like, seems like we've had a few of those already. But this is often called the first isomorphism theorem, or just the isomorphism theorem. All right. And I'm not going to state that to start with. I'm going to have a little bit of a discussion here, hopefully leading up to it. All right. So the first thing I just want to talk to you about is a little bit of set theory, and just the idea of, you know, the problem. Suppose you're given a function, right? You have a function, and you had a function from, let's say, A to B, you know? Right? And maybe A looks like this, yeah? I don't know. Then the question is, how can you take this given function and make it into a bijection, right? What can you do? I mean, how do you make this function into a bijection? Well, one easy thing you could do, of course, is whatever we're going to create here, instead of putting B, if we just put, you know, f of A over here as the codomain, well, then it's going to be surjective. That one's kind of easy. You just get rid of all this pesky other stuff that we put in the codomain that you've been wondering why it was there ever since we introduced this concept of codomain back in Math 200, right? What's the deal with the codomain anyway? Just making this annoying surjective problem that's always vexing me, right? So setting that annoyance aside, then the question is, whatever arrow I'm going to draw here, how do I make the thing I'm about to draw one-to-one, right? See, the problem with the given function in terms of not being one-to-one is what? If we look at, you know, f inverse of B, what is that? That's A and A such that what? F of A is equal to B, right? This is the so-called fiber of B. Under with respect to F. So it's a set of all points in the domain which map to B, right? And you had a homework problem early on where I asked you to prove that these fibers, the non-empty fibers at least, partition the domain. We proved that if you have two different fibers, well, they're distinct, right? And you can find a fiber covering every point in the domain. So something like this is a picture we could make, yeah? Like, I don't know. Maybe this is a typical, in my just heuristic picture here, this is an inverse, you know, the fibers partition the domain, right? So if I want to make the function, if I'm trying to create a one-to-one function from the given function, what I need to do then is to somehow get rid of this problem of more than one thing mapping to one thing, right? So the simplest thing to do is to take what's called a cross section, right? And a cross section would be something like, just you know, pick something like this, and you know, just pick one thing from each fiber, and you know, we could call this thing, I don't know, S of A, and a section of A, and then you'd have this new map F bar going from the section of A to F of A, and this F bar defined by F bar of X equal to F of X for all X in the section of A, that would be a bijection. Because what we've done is just, you know, gotten rid of the ambiguity in terms of the fiber. We just say, okay, well, we'll just take one thing that maps to each thing in the range, right? And then by construction, this would be a bijection, right? So this idea I'm sharing with you has nothing to do with group theory per se, right? This is just function theory, just set theory, yeah? But this story plays out in group theory and gives us what's called the fundamental, the first isomorphism theorem, right? But it also meaningfully involves the other concepts we've been talking about, like normal subgroups and so forth. Here, to give you an example from complex analysis, which before I get to the group theory, here's an example from complex analysis. If we had f of z equals to e to the z, right, where that means e to the x, e to the iy, which is e to the x cosine y plus I e to the x sine y, this is so-called complex exponential, then you could ask what's the inverse image of a point, what's the inverse image of some particular complex value? And I'm come up with a name for it, say W naught. What's that look like? So the answer is, it looks like log of W naught. Now log of W naught is actually the natural log of the absolute value, the natural log of the modulus of W naught plus I times the so-called argument of W naught. Right? And this argument of W naught is the principal argument of W naught plus 2 pi z. It's actually a whole set of values. So here, the way it works is W is equal to the modulus of W times e to the I arg W. So this is an identity that we learn in complex analysis. But I haven't had complex analysis, and I'm not planning to. It's okay. So far, you're not past the first lecture, more or less. All right, this is all in the first lecture. Let me show you how it works. So if we calculate f of anything, f of the natural log of the modulus of W naught plus, I theta plus any multiple 2 pi j. Well, that's going to be e to the natural log of the modulus of W naught plus I times theta plus 2 pi j. And here I'm given, so that I don't keep writing arg, I've just called this thing theta for the sake of discussion. I'll stick a knot on it. Why not? There we go. So what happens by definition of complex exponential? This is e to the natural log of the modulus of W naught, and then you've got cosine of theta naught plus 2 pi j plus I sine of theta naught plus 2 pi j. What do sine and cosine do to integer multiples of 2 pi? They just absorb them, right? Because the 2 pi periodicity of sine and cosine. And so here we've got e to the natural log of the modulus of W naught cosine theta naught plus I sine theta naught, which is, by the way, modulus of W naught e to the I theta naught, which is to say that it's W naught. So there you go. That's a proof that the inverse image of W naught is in fact given by the little logarithm of W naught, which is a set of values. In fact, it's an infinite set of values. If you want me to picture this, what I'm showing you is that if we go from the z plane to the so-called w plane, as it's often called in complex analysis, and we use the exponential, the map, if I pick a w naught over here, right, what is it coming from? It's coming from everything in the little log, right? So just to be specific, if we looked at w naught equals to, I don't know, let's say it's 1 plus I, just to be specific. If we have w naught as 1 plus I, then what's the length of 1 plus I as a complex number? what's the modulus of 1 plus I? The so-called length of it is a complex number. Square root of 1 squared plus 1 squared, which is square root of 2, right? So in other words, little log of 1 plus I is natural log of the square root of 2 plus I times, and the angle there is 45 degrees, so pi over 4 plus 2 pi k. So going backwards and spending entirely too much time on this example, natural log of the square root of 2 plus I pi over 4 is like, I don't know, where is that? 0.6-ish, it's somewhere in here, let's say. Pi over 4 is about, so I think the first value is in here somewhere, all right? And then the deal is, every 2 pi, there's another value. And this goes on, and 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 so forth. If I was a taller person, I could draw the whole fiber, but the fiber is an infinite set of points, right? Infinite set of points. And they're all mapping to that one, W naught. Right? So this is not just, the complex exponential is not just 1 to 1, it's infinity to 1. All right? There's infinitely many points mapping to that one point. All right, so just an example outside of group theory for a second, although, you know, we have played with the imaginary exponential, we've seen that it can be used to create groups, right? We've created, for example, the circle group with this thing in the complex numbers. All right, so here's a fact. If phi is going from, let's say, G1 to G2, and if phi is a homomorphism, all right, then quiet in the back. Yeah, you heard me. That's right. I'm going to throw a marker at you. You want me to throw a marker at you? Oh, okay. So I can do that. Then fibers of the domain of phi are cosets of the kernel of phi. I mean, this is a fact we could prove. All right? Consider this. If we have, what's the condition for x and y to be in a fiber? What would it mean for x and y to be in a fiber? That would mean that phi of x is equal to phi of y. This would mean that x and y are in same fiber, right? But what does that tell us? That tells us that phi of x, phi of y inverse is equal to E. But remember, the properties of homomorphism tell us that phi of x, y inverse are an element of E, right? I mean, equals to E, which says what? That says that x, y inverse is an element of the kernel of phi, right? And what's that mean? That means that x kernel phi equals to y kernel phi by our work on cosets, yeah? So for a homomorphism, fibers are as big as the kernel of your map. All right? Actually, I should confess, my first example actually is a homomorphism. Right? You can prove that f of z plus w is e to the z plus w, which is e to the z times e to the w, right? So in fact, F, if I'm to be truthful with you, is in fact a homomorphism from the complex numbers under addition to the non-zero complex numbers under multiplication. In fact, it is a homomorphism. And so, what's its kernel? Well, I still have some homeworks to write for this part of the course. Maybe I'll put it in there. All right, let's move along. So this is very interesting that the fibers are just as big as the kernel. If you thought about the wild world of all possible maps, it would certainly not be that. I mean, generally speaking, fibers can be different sizes. They don't have to be like the same thing over and over again like a coset, but they are here. And so this brings us to, moving it along here a bit, definition. If H is a normal subgroup of G, then the natural, let's see, what is this usually called? Natural coset map, or is, and this is a, so pi here goes from G to G by H, which is the factor group. Is this defined by what? What do you think what's the rule? Pi of G equals to what? I will take your G plus H and make it G. But yes. So I want to think multiplicatively here. But yes, often it would be G plus H if we were working in an additive context. I wouldn't take that from you. And we have a theorem. Yeah? Theorem is this, is that pi from G to G mod H as above is a homomorphism. Right? And more than that, what's its kernel? What's the kernel of pi? Like it's, I don't know, is it the crust? Or is it the inside? Like what makes a pi a pi? I don't know. Too soon? Sorry. Still the shadow of the test still over us. I don't know. All right. Let's move along here. So pi of, let's say, I don't know, AB is equal to ABH is equal to AHBH, which is pi A, pi B. There you go. That's the homomorphism property, right? What's the kernel of pi? So here we're looking for G and G, right? Such that pi G equals to what? H, right? So what is this? This is just the condition that GH equals to H, which is what? That's true if and only if what? G is an element of H, right? By our study of cosets. So in other words, this is precisely H. So the natural map is a homomorphism, and its kernel is the normal subgroup, which we're mapping to the factor group of. Now, I have an example. This is a kind of important example. Let's see here. So if we look at G equal to the integers and look at the subgroup H equals to NZ, then the natural map pi of x is just equal to what? Now we've got x plus NZ, yeah? Because additive, right? And so this is a homomorphism. And what's the kernel of pi? It's just NZ again, yeah? All right. So there's a theorem that essentially says that, this concept we've been playing with of normal subgroups, it plays nice with the concept of isomorphism, all right? So let's prove this theorem. In other words, if I have an isomorphism, it's going to appropriately transfer the concept of a normal subgroup, right? So like the image of a normal subgroup is going to be a normal subgroup. That's not quite true. There's a little bit of fine print there. You'll see why. So if we have phi from G1 to G2, a homomorphism of groups, then one, if phi of G1 is equal to G2, right, and H1 is a normal subgroup of G1, then the image of H1, namely phi of H1, is a normal subgroup of G2. So I did have to assume that phi is a what? What's the fine print I was talking about here? In contrast, the inverse image of a subgroup of the codomain is a normal subgroup of the domain, no condition on phi other than it be a homomorphism. I did need, what have I written here? Okay, what's this in words? You guys know? What's that mean? Phi is a what? Or phi is onto, right? It's a surjection. All right, so let's prove this theorem. Let's start with number one. So assume that phi is a homomorphism, and phi is assume the data in part one that phi of G1 is equal to G2. So we're going to assume that phi of G1 equal to G2. And also that H1 is a normal subgroup of G1. I'm aiming to show that the image of H1 is a normal subgroup of G2, right? So how would I do that? Let's say Z be an element of G phi of H1, G inverse, where G is an element of what? G2, yeah? What I would like to do is to show that Z is necessarily where? What do I want to do? What does it take to show that phi of H2 is a normal subgroup of G2? I need to show that it's fixed under conjugation by arbitrary G in the codomain. In other words, I need to show that that Z is again in the image of H1, right? Now here is why the surjective condition is needed. Because phi is surjective, I can write G as what? This says that there exists an X in G1 such that what? Such that G is equal to phi of X, yeah? Hey, Watch it, mister. All right. Sorry for the distraction. It was for a good cause. So G is phi of x, right? So we now have Z is equal to phi of x. Oh, what does this say? I'm sorry, I've forgotten another point. This says that Z is equal to what? G phi of h, right? G inverse for some h in where? In h1, yeah? That's what it means for Z to be in that set, G phi of h1, G inverse, right? There exists an h in h1 such that that's the case. So then Z is equal to phi of x, phi of h, phi of x inverse, yeah? And then by properties of homomorphism, what do we got? That's actually phi of xh times phi of x inverse, and then one more step. This is phi of xh x inverse, yeah? But you notice that x, h, x inverse is an element of x, h1, x inverse, right? And by the normality of h1, what do we get? That's a subset of what? This is a subset of h1, since h1 is a normal subgroup of g1, right? So what have we shown? That gives us then that Z is equal to phi of something that's in h1. So Z is equal to phi of xh x inverse, where xh x inverse is an element of h1. Therefore, Z is an element of phi of h1. Yeah? Which does what? That proves then that, therefore, G phi of h1, G inverse is a subset of phi of h1. Therefore, phi of h1 is a normal subgroup of G2. And you can see why the surjectivity of the homomorphism was necessary, right? Otherwise, I wouldn't be able to make that link with the conjugation in the domain. All right? Questions? Comments? Oh, wait a minute. No comments. Never ask for... Asking for comments is dangerous. Never ask for comments. You might get some. Now, let's prove 2. The proof of 2, let's see here. We're going to assume what? That H2 is a normal subgroup of G2, and we would like to show that, well, that's what we're going to assume. Then suppose that Z is an element of what? I can't read my own writing. G phi inverse, yeah, of H2, G inverse, yeah? What's our goal? Our goal is to show that we want what? Want to show that Z is an element of, in fact, phi inverse of H2, because that will then imply that, you know, G phi inverse of H2, G inverse is a subset of phi inverse of H2, which will then, by definition, prove the normality of the inverse image of H2. Right, that's what we're after. It's probably a good idea to just write down what this means to guide our work a little bit. What does that mean? What does it mean? What does it take? If Z is in the inverse image of H2, what's that mean? What's that say about Z? This means what? Phi of Z is where? Yeah?
Are all of those H's H2s?
Yes.
Kind of hard to read.
Yeah, they're all H2s.
Okay.
It's, yeah, my writing up there is not awesome. So yes, so phi of Z should be an element of H2. Yeah, they're all 2s. 2, 2, 2, 2, 2, 2, 2. Yes. But some of them are 2 base 10. Others of them are 2 base 11. Ah, no response. I like that. You've grown immune to my nonsense. I'm happy. All right, so phi of Z should be an element of H2. That's what it means to be in the inverse image of H2, right? It maps to H2. And so to say this right here, right? So what does star mean? Star means that there exists what? There exists, let's say, H in G1 such that what? Phi of H is where? Is in H2, right? And Z is equal to G, H, G inverse. That's what star means. There's something in the inverse image, H, such that that conjugated by G gives me Z. So, great. Consider that, well, I guess we should probably look at phi of Z. That's what we're after, isn't it? What's phi of Z equal to? It's phi of G, H, G inverse, which, by the way, is phi of G, phi of H, phi of G inverse, right? And what are we looking at here? We're looking at something in H2, right? And these guys are where? In G2, right? But H2 is what? It's a normal subgroup of G2, which means that this is an element of, well, I mean, this is an element of phi of G, H2, phi of G inverse, which is, by the way, a subset of H2 by H2, a normal subgroup of G2. So what have we shown then? We have just shown that phi of Z is an element of, oh man, I'm sorry, Emily, that red is really hard. Yeah, we have shown that phi of Z is an element of H2, yeah? I'll write it again here. Thus, phi of Z is an element of H2, right? Which is what we were trying to show. Hence, Z is an element of phi inverse of H2, and so G phi inverse of H2, G inverse is a subset of phi inverse of H2. Therefore, phi inverse of H2 is a normal subgroup of G1. All right. Sorry, I think I'm spending too much time on this one. I should probably move along. They're up to something. So can you guys think of an important application for this part 2 I just did? How about what's an important subgroup of G2? how about this? E2 is a normal subgroup of G2 for a homomorphism from G1 to G2, right? Thus, the inverse of the identity in G2, which, by the way, is what? That is the kernel of phi, is a normal subgroup of G1. Wait a minute. You mean to tell me that all we have to do to prove a subgroup is normal is to produce it as the kernel of a homomorphism? Yes. That's pretty nice, isn't it? Because it's not hard to come up and prove things are homomorphisms. It's considerably more work to actually prove what? That the subgroup is normal, right? That's kind of a drag. Showing something's the kernel of a homomorphism, that's pretty easy, and that suffices to prove that that's a normal subgroup of whatever, what you're looking at. So that is like very, very nice result, independent of the theorem which I'm about to write down, which is the isomorphism theorem. Here's the theorem. And I motivate it. Well, I think I motivate it. I give some pretty decent, I think decent motivation in the notes for why this theorem should be true. So a rough intuition for it, I'm having trouble formulating today. For some reason, I'm distracted. Some reason. Theorem. All right. So this is theorem 3.5.7. Suppose phi is a homomorphism from G1 to G2. All right? Homomorphism of groups. Homomorphism of groups. I should do what? Ooh, I should.
It's the last 5 minutes over and over.
That's pretty good. I like that, Sarah. Does anyone want to chaperone my children over to Sopranos class? All right. You're in charge, Morgan. Follow the nice lady over to Dr. Sopranos' house. Class. What?
Right now or in 5 minutes?
And we'll, yeah, with 5 minutes. In 5 minutes. 5 minutes. Yeah. One over. Yeah. Okay. I do. Let me finish. This is. All right. All right. Hem. So G1 to G2 homomorphism groups. Then phi bar, and I'll define phi bar here shortly. That's going to go from the G1 mod the kernel. How do we know that G1 mod the kernel even makes sense? What did we just prove about the kernel? It's normal, right? So the factor group by the kernel makes sense. So this, by the way, and if you think about it, well, that's not exactly a cross-section. It's the same idea as the thing we started class with. Because if you think about the coset space, what are we doing? We're thinking of all the points in each coset as being the same point, right? So that's another way of removing that departure from one-to-oneness in the map, right? By working with cosets instead of points, that removes the lack of one-to-oneness, if you will. And so it's going to be injective if we make that the domain. And, well, we made the codomain the image, so it's automatically surjective. That's going to be an isomorphism. That is an isomorphism. I haven't really said anything yet, though, because I haven't told you what. The formula, right? Given by phi bar of, well, it's a coset, right? So let's say G kernel phi is equal to just phi of G, right? For all G kernel phi in G1 kernel phi. So, equivalently, you could replace this condition with what? Like for all G in where? In G1, that would be equivalent, yeah? So this is an isomorphism, and what else? So the punchline here is that G1 mod the kernel is isomorphic to the image. So that's the isomorphism of the isomorphism theorem. So what's there to prove here? We've already proved some of the theorem, right? So proof, we have kernel phi normal subgroup of G1, thus G1 mod kernel of phi is well-defined factor group, right? So we have that. And suppose that x kernel phi is equal to y kernel phi. Then what? Then phi bar of x kernel phi is what? Is phi of x. And phi bar of y kernel phi is equal to phi of y, right? So what does that say about x and y? Well, let's say it this way. Since phi of x equal to phi of y, if and only if what? Phi of xy inverse is equal to e, right? Which is equivalent to what? If and only if what? Xy inverse is in the kernel of phi, right? If and only if what? X kernel phi equals to y kernel phi. What does this prove for us? Go with the nice lady. She's going to take you to a magical land.
Literally run around.
What's that?
Do you just want me to have them literally run around?
Tell them to do a lap.
All right, he's going to go over. So let's give him like 3 more minutes before we go over there. We'll crash the last 2 minutes of this class. I won't be a monster. It's you. So what this string of equivalences shows you is that phi bar is single valued, right? If I have the same input, I get the same output. Whenever you define a mapping in terms of a coset, you should stop and ask yourself, is it actually a mapping, right? This is. So we have a function, phi bar. By construction, it's onto, right? And what's left to show? I mean, we'd like to show it's a bijective homomorphism, right? So is it injective? I think what I have on the board also shows that it's injective, right? Because if phi of x, let's see here. Phi of x kernel phi equal to phi of y kernel phi bar of x kernel phi equal to phi bar of y kernel phi implies phi of x equals to phi of y, which is true if and only if the inputs are equal. So this actually shows 1-to-1 as well, right? What's left to show is just the homomorphism property. So how about that? Phi bar of x kernel phi, y kernel phi is phi bar of xy kernel phi, which is phi of xy, which is phi of x times phi of y by the homomorphism, which is, by the way, phi bar of x kernel phi, phi bar of y kernel phi. All right, so with the exuberance of my children, I may have forgotten a detail or something, but I hope you can see this is most of the proof of the first isomorphism theorem. Now, the applications of this theorem are many, right? see if we could think of maybe, let's see here, I was joking about the anti-symmetrizer with you guys the other day, wasn't I? What was the anti-symmetrizer? I'll do this example and we'll be done. If we took phi of A equals 1/2 A plus A transpose, A minus A transpose, yeah? Then you can check that this defines a mapping from n by n matrices to n by n matrices. And I'll take them to be real just to, well, keep it real. And so is this a homomorphism of these additive groups? Excuse me, multiplicative groups. Wait a minute, multiplicative, no. Give me a second here. I got to come to terms with where I am. Additive. You know, is this a homomorphism of these additive groups? All right, guys, go with the nice lady. When you get to the new room, run in circles. Run in circles. It's very important. That's right. So, this is a homomorphism, right? In the sense that phi of A plus B is equal to phi of A plus phi of B, yeah? It's a homomorphism. What's its kernel? So the kernel is what? It's A, such that 1/2 A minus A transpose. So what's the kernel of phi? It's the symmetric n by n matrices over the reals, right? And what's this give us? What's the image, by the way? You can prove that phi of Rn by n is in fact the antisymmetric n by n matrices over the reals. And so homomorphism, kernel is the symmetric, range is the antisymmetric, and this gives us that this is isomorphic to Rn by n mod the symmetric n by n matrices. Now, you may recognize this example from linear algebra. It's pretty much my favorite example. It was probably on your final. I mean, odds are pretty good for it. But the first isomorphism theorem is such an important tool, and I will show you more examples of it as we go on. So I guess we're done for today. Thanks, guys. Oh, I have your